of students panic when it comes to problems about hydrostatic force. If it speaks to you, I completely understand. These types of problems typically require several steps to finish. In today's video, we are going to review a classic hydrostatic force problem. So here we have a water gate connected to a hinge. The hinge is 3 meters below the water surface. The gate is 6 meters tall and 4 meters wide. On one side of the gate, it is the water. On the other side, it is the local atmosphere. From the figure provided here, it is very clear that hydrostatic pressures are applied to the left side of the gate, creating a counterclockwise moment. If we don't have a clockwise moment to balance it, the gate will be pushed open by the water. It is a typical situation when water dams release water downstreams. So if we want this gate to completely shut down and keep the water in the reservoir, we will have to install a stopper at the far end of the gate. Applying the stop force at the far end allows us to take advantage of the longest moment arm, which makes it possible to create the desired turning effect with the smallest force. Back to the problem we are working on, we are trying to find the force at the stop, neglecting the weight of the gate. How are we going to answer it? Let's apply the from the end to the beginning method. The system is at equilibrium, meaning that the clockwise moment introduced by the stop force at the far end of the gate is balancing the counterclockwise moment created by the hydrostatic force. This is our starting point. As we know, that moment is the product of force and moment arm length. By balancing the moment around the hinge, we now have the overall moment around the hinge equals to the clockwise moment introduced by the stop force, plus the counterclockwise moment created by the hydrostatic force, which now has a negative symbol if we set being clockwise is positive. And this overall moment around the hinge equals 0 at equilibrium. Now we can rearrange this relationship to find the expression for the stop force, which could be directly calculated if we know as few as 3 independent parameters. And these parameters are, first, the height of the gate, h. This is directly given in the statement. H equals to 6 meters. Second, the resultant force of the hydrostatic pressure, F sub r. We don't have it in the statement, but we'll be able to find it using hydrostatic equations, and we'll be working on it shortly. Third, L sub r, the length of the moment arm linked to the hydrostatic force. This is another unknown at this moment. As explained in another video, the hydrostatic force acts at the center of pressure, not the centroid. Therefore, this moment arm length will be distance from the center of pressure to the hinge. And we'll be taking care of this parameter as well. Alright, now let's start with the hydrostatic force. As discussed in another video, the hydrostatic force can be calculated using the pressure at the centroid times the surface area. And the pressure at the centroid is simply the product of the specific weight of the fluid and the depth of to the centroid. Now, from the figure, it is not difficult to see that the depth to the centroid can be calculated using a little bit of geometry. Now pause this video here so you can take a closer look at this step. The surface area of the gate is simply height times the width. So we have 6 meters times 4 meters equals to 24 square meters. Finally, using the specific weight of water, 9,810 Newton per cubic meters, Since temperature information is not given, we now have the hydrostatic force, approximately 1318 kilonewton. Next, let's tackle the length of the moment arm, and this is the distance from the center of pressure to the hinge. We talked about it in the previous video. Now to find the center of pressure, we will need the slant distance from the centroid to the water surface y sub c. And we'll also need the moment of inertia through the center of the turning surface around the turning axis. So I sub xc. Now you can pause this video and see how to calculate these two parameters. From the distance, for the slant distance, you will need to apply a little geometry knowledge here. And to determine moment of inertia, the relevant equations can be either derived from calculus or found directly from almost all textbooks and reference manuals. These equations will also be available for your FE or PE exams. Note that what we got here is the difference between the center of pressure's slant distance y sub c and y sub r and the centroid's slant distance y sub c. The distance from the center of pressure to the hinge will be calculated by adding this distance difference to the distance from the centroid to the hinge. I know it sounds like tongue twisters as I speak, so I highly recommend you pause this video for a minute and take time to digest this part. Alright, until now, we have found the hydrostatic force F sub r and the length of its moment arm L sub r. And we know h, the moment arm length for the unknown force. Now let's not forget taking all these values to solve for the force at the stop. Eventually, after all these steps, we can determine that the force at the stop should be around 761 kilonewton. If you want more videos like this, focus on how engineers actually think on exams, like this video, subscribe the channel, and comment below with topics you would like me to cover in future videos. And I will see you in the next one.